Okay, welcome everyone to my continuation of what is algebraic graph theory. Today we continue our story about random graphs. In particular, I would like to talk about the diameter of a random graph. I will explain what the diameter is on the next slide. But again, you should think of this as being like, what are diameters, what are certain properties, not just of random graphs, but random graphs model something like a generic graph. So if you draw a graph randomly, or almost all graphs, so what kind of properties do they have? And this one is a really fun one that I like a lot. It's quite easy to explain. So the diameter will take values in n. That will be quite obvious from the definition on the next slide. But it turns out that almost everything has a certain fixed diameter d, which is just very far away from being everything appears. It's more like just one value appears. It's kind of really crazy. So in principle, everything could appear. And certainly you will find graphs such that the diameter is arbitrarily large, but almost all graphs have the same diameter. It's kind of a very fun statement. So what is a diameter? So the notion is just how large the graph is, if you want. So my diameter d is just, well, the maximal distance between two vertices. And I'm kind of ignoring the case where d is infinite. So when the graph is not connected, let's ignore that. But anyway, otherwise you just write down, well, here's my graph with 1 to up to 7 vertices. So you write down the 7 by 7 matrix in this case, and the lengths of the shortest path. So from 1 to 1, shortest path. So on the diagonal, shortest path is always 0. Let's say from 1 to 5. From 1 to 5, the shortest path is of size 2. Let's do another one, maybe from 6 to 2 is also boring. From 7 to 4, the shortest path is of length 3. There you go, and you just write it down. From 7 to 2, the shortest path of length 4, and so on. And the diameter is just the maximal number you see. So the diameter of the graph is 4, because you need to go 4 steps, at most 4 steps between any two vertices, right? This is how far the graph stretches, if you want. Right? Graph is an abstract object, it doesn't really live anywhere. So this is kind of how we think about how far it stretches. That's why it's called the diameter of the graph. And this clearly can take any value you want, because just think of a line graph, right? So if you draw a line, then the diameter will just be the distance from between the two extreme vertices of that graph. And that can be arbitrarily large, because you can just draw your graph arbitrarily large. Okay, this thing takes any value. And let's have a look whether actually it takes any value really for almost all graphs, or maybe it actually doesn't. So let's have a look. I already spoiled the story anyway, so it doesn't take all values. Anyway, we will have a look. Remember my slogan that random graphs, or almost all graphs, have very, 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 very many edges, like many, 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 many edges. So if there are many, many edges, then the diameter should be actually pretty small, right? Because, well, 2 vertices or 3 vertices here, there will be trillions of edges going in somewhere, right? So it's very likely that it will end up, those 2 vertices here end up very close by. That seems to be very likely. The expectation I would actually have here is the diameter should be quite smallish. But how tiny precisely? 2, 3, maybe some bound, depending on the number of vertices or whatever. Diameter 1 doesn't work. Why the diameter 1? Diameter 1 means there's one edge between all vertices. So that's exactly the complete graph, right? So one edge between every vertex, only the complete graph has diameter 1. Right? One edge between each vertex, because you need to go at most 1 step from any vertex to any other. Okay, but otherwise it's a 2, it's a 3, is it bounded? That's not quite clear, but we expect it to be very tiny, because, well, there are many, many, many edges. And what can you do if you want to answer that question? Well, you can just ask a machine, right? So you list all graphs, or in this case, I just randomly generated 10,000 graphs with 10 vertices, top picture, or 10,000 graphs with 50 vertices, bottom picture. And just list it, or just ask the machine what is the diameter of the graph. And for 10 vertices, you still have some low number coincidence here, so you can't really tell whether it's 2 or 3. Certainly it's not 4, and certainly it's not 5, and there wasn't even anything bigger than 5. Mind, you that I used 10,000 graphs here, and there was nothing bigger than 5. So large numbers are essentially completely unlikely. And it's only up to deciding which one it is. And if you increase the number of vertices, it becomes pretty clear. You almost can't see anything else anymore. So with 50 vertices, there was not a single graph with diameter more than 3, and only like a handful of diameter 3. And essentially everything was diameter 2. So diameter 1 is the smallest possible, but it will not appear because this would just mean there's only one graph on a certain number of vertices with that diameter. And we're looking for almost all graphs that have a certain diameter. So that can't appear. But the second next to the next one, the next possibility, it's kind of the tiniest possible value. It is 2, the tiniest possible value, ignoring this value 1. And this is, of course, just the computer verification, or this is just a computer kind of conjecture, if you want. But of course, you can just prove that. I mean, it's not so difficult then. So let's say they are constant, and there are certainly statements when they are not constant. Then the diameter of both of our random graphs is always 2. So almost all graphs have diameter 2, which is, I think, is a really fantastic statement. Almost all graphs have diameter 2. That's very, very great. And turns out, so I think this was a really cool idea eventually. So you think of this in a real world setting. So there's this idea of a small world, like on Facebook, everyone is related to everyone by at most whatever how many edges. And that seems to be related. So kind of you could think of like the Facebook graph or any social media maybe, or the World Wide Web, the connection between websites. They all have very tiny diameter. This is exactly the small world effect. So if you're living in the United States, you might have heard the 6 degrees of separation, something like that. Small world. So kind of social networks and things that turn up in kind of whatever the social sciences tend to have very, very, very small diameter. So this is suggesting, and people thought about that, it looks to me like this is suggesting that those graphs, like the connection graph on Facebook, where you have all Facebook users and you draw an edge between them if they are friends on Facebook, this graph has very small diameter, so maybe it is actually a random graph, because this seems to be a property of random graphs, very small diameter. And people thought about that for a long time. And well, people thought about it for a long time, and then realized quickly. People thought about it and realized quickly that it's actually not quite true. So a random graph, and the difference is the following. So a small world graph, in the very same way as a random graph, has a very, very, well, in this case, it's a mean path length, which is kind of the average instead of the max, but it doesn't really make a difference here. It's very, very tiny. So that's what fits, and a kind of a more regular graph usually has a very, very high or long mean value or distance. But it turns out, and this is kind of what these Facebook graphs tend to do. So here's a more real world example of a Facebook graph. They have very, very small diameter, but they look very, very far from being random, because there's something they have which the random graph doesn't show, and that's clustering. So the clustering of a small world graph is really, really high. So there are a lot of, well, like on Facebook, there will be people with lots of friends, and a lot of people are connected to them, like in this picture here. So this person has a lot of friends and so on. And that's what kind of makes the graph so small. And there are a lot of edges, there are a lot of vertices, which don't have so many friends, actually, like a lot of leafy things. Anyway, so that's more like how those small world graphs look like. And that's very far away from random, right? This is not what comes out of a random model. A random model will produce that crap here, which is just blur, essentially. So there's something different, and people nowadays use different types of random models. So not the ones I was addressing in the past few videos, but different ones, exactly for the reason that you want clustering. But it's in a certain sense, Facebook and friends are still random, but just not in the sense we discussed here in the video series. Anyway, let's come back to the diameter, because I think it's a pretty cool statement. The diameter of almost all graphs is 2, right? Which is kind of a little bit of a shocking statement. Anyway, I hope you enjoyed this video, and I also hope to see you next time.